Oh, it's not working. Let me disconnect and reconnect.
Okay, good that we had last presentation, so you have time.
Yeah. So you have enough time to fix that. Yeah. Okay, so let's start the meeting. Good afternoon, everyone. This is the second working group meeting of the SRv6 Ops working group. So welcome you join us. And let's start from a note while. I think we require everyone to read the note while carefully, especially there are some content related to patents and code of conduct. And we also give some detailed note really well. And please read those text by yourself and keep professional within the meeting. And for the in-person participants, please also log in your Miteco. Please also sweep QR code. For the remote participants, please make sure your audio or video are off unless you are presenting during a session. And so anyone can volunteer to take a minute. Okay, Shannon and Chengli, yeah, thank you. Okay. And when you have comments, please join the comment queue via Miteco. And please use the mailing list actively. Okay, so for our first milestone, we hope to adopt a document describing operational and management issues during SRv6 network deployment. Now we have had a candidate document. We have listed here. Please review it. We really need your comments and feedback. And now Spring Working Group is working on SRv6 operational security draft. And please also provide your feedback. So here is today's agenda. We have 4 presentations from different operators. Maybe Drew, please.
Yeah, thanks. So we have like a 1 hour. So we have various different operators from enterprise, from power grid, from different regions coming and sharing that experience. We also had informal side meetings between the authors just before that. So this time we are not discussing the documents, but maybe in the future meeting, our hope is to prioritize documents. But this meeting, we are focusing on operator presentations. So we have 4 operators. We request each of them to take around 10 minutes and keep some time for questions so that we can have a good discussions going forward. So with that, let's invite our first speaker, Daniel from Bell Canada. And let me load the slides. Hello. Hello.
So I'm going to talk about the service programming, the implementation at Bell. that we did, and it's part of the deployment drafts existing, and it's aligned with two existing, multiple existing drafts or RFCs in the SRv6 architecture. Both the service programming, which I hope at some point will be actually adopted finally, and then the network programming architecture. So the design process behind this has always been around the fact that how do we create telco service constructs? Industry-wide, you have basically three that we talk a lot about in the industry from a telco perspective. We have the subscriber session steering that we see happening, or the traffic steering. We have the service chaining approach, where how do you create an inline or value-add service, and then the traffic engineering. In reality, if you look at this, it's always kind of the same requirements, design principles, but we always treat them separately. So how do we design in a single architecture? And but each of them, they require some kind of control plane functionality to be able to achieve the expected results. That was the initial process around the design. When I started to work on this, and then we introduced in our network, it says, well, how can we rethink the way we think about service composition? Because, and this is where SRv6 really shined for us, because it implemented the capability of doing policy constructs. And the way we're able to do it is extend from any kind of network design, but also to the application on the host level, which from a long time was one of our goals with SR and PLS as well. We realized that with the network programming architecture, without necessarily having everything being an IETF standard, the standard itself gave us the right tools to build systems. And I know there's a lot of drafts happening right now in IDR to create service construct and create the control plane pieces and add extensions to BGP. Actually, I was one of the co-authors in the experimental draft on LS services. But how could we do it in a way where we don't necessarily need to always add the new protocol? If the protocol works, there's tweaks we can do with it. And how could we do something which is more cloud and SDN approach? Because basically, we're trying to merge both domains of cloud and workloads with the network. Example use case, this is a typical GI LAN service we have in a mobility network. We do basic MacGyver-esque approach of doing PBR, TOS routing, TOS selection. We do EVPN sprawl across multiple functions. We do routing. We do everything. And it's something which is quite expensive to deploy and to maintain. And then you realize that if you want to grow this across cloud providers, it's impossible. And if you want to try this at a level where you want to distribute your functions deeper at the edges of the network, you need to reduce the cost. Those kind of design principles are too expensive. You can't do this at scale. So we looked at the way of how do we do a GI LAN implementation separately. So we use a stateless traffic steering using SRv6, and we introduce a proxy function to be able to attach network functions into the path. The SRv6 proxy actually creates the logic of a chain constructs and not just one element. So we try to avoid recirculation and creating binding SID that we need to decompose after. We can use the same logic on both cloud providers' infrastructures in our own infrastructure. And we have, since it's SRv6, we have no dependency on a control plane. So we start with BGP route coloring, but we can evolve to an SDN-like approach, or we can do GitOps if you wanted to. We have various flexibilities. And actually in numbers, we validated that we ended up with an 80% cost reduction around how we do things by doing that design compared to piling up a bunch of equipments and vendor device and software and trying to make them mix and match. The logic is really around how do we traffic steer. Actually, the logic is we are able to attach with any access network or network through the gateway capabilities of SRv6, interrupt into the interrupt ongoing work, but then we can map by doing route coloring the targeted traffic we want to support. And then we send the traffic we steer to an explicit path into the proxy function. And the proxy is able to decompose into XYZ chain, whether it's a one function, two function, we don't really have no dependency. And then once it's finished, you do the rest of the SRv6 operation, either penultimate segment pop or like the ultimate segment drop, if it's the last one in the chain. And then we go back on our merry way with the VPN constructs. The reason for the proxy is, well, the day one, when we started to work on the service programming functions, that the proxy is essential. First, we cannot assume that at some point everybody will agree to build an SRv6 aware function or a SRv6 capable function. That's the learning from NSH and SFC, which we never finished having like a real function that actually supported it. So assume the worst, build for proxy functions. And then with this, I can create multiple variations of a capability, and you can avoid data path recirculation, as I said, and we can create independency because some functions in security, for example, they don't want you, they really want you to know that they're existing in the network. They don't want to be advertised. So you cannot make them part of a network control plane. You need some abstraction. It also introduced something which is interesting if you do a proxy function, which is like availability. Can you measure that the function is still working? If it's overloaded, can you route traffic across? And what happens if there's a failure in the chain? If function fails, do you kill the policy or the path, or you just let it go open? That the proxy was able to give it to us through some gRPC or a Yang model that was developed in our systems. And the fact that now it's a SRv6 and the goal was to extend to any cloud, the work that was done with extending to a CNI and Kubernetes, then I have the same logic around how we can create service construct from a workload application in any cloud. We're using SRv6 and be able to attach it to an end function we have in our network using the same logic. The steering now happens at both edges of the SRv6 domain without necessarily having to do a midpoint insertion if I wanted to do it. So, and the logic applies for cloud, applies for our traffic inside the wireline services. And if you look at this, extensions to what's being done in broadband forum with subscriber session steering is actually the same logic. So it's just an extension. I'm good for questions if you have any at the moment. I think this was pretty much it. I did it in 3 minutes. I'm actually, you have a lot of time for questioning if you want to.
Let me cancel the timer. Yes, folks. Questions for Dan? Please join the queue. Yes. Yes, please. Yeah.
Hi, Yolio from ZTE. I found the NSC function very interesting. So what's the actual behavior of this sysad?
Yeah, so basically, as I said, if you want, I'm going to go back to the right slide.
Yeah.
So in network programming, the logic was in network programming, if you have a SID function, a local SID behavior that you create at your node, you can pretty much do what you want. Like the logic from SRv6 is if it's local to you, do what you want with the SID instructions. So we created our own, saying instead of doing a binding SID, that's right, you need to decompose into multiple segment SIDs, or having to do recirculation and go across the zigzagging loop of recirculation into the data path. We said, let's create an independent function that actually maps functions together. So the function attached together as they are in the proxy attachment part, the data path. But then we just use one SID to explain the chain. So I have a function of 3 functions. It's one SID for 3 functions. If I have a different policy with 2 functions, it's another SID for 2 functions. And then I can scale this to an infinite amount depending on the number of the local SIDs I use.
So one set for each function?
One SID for one for every chain. So if I have a chain of like, if I was I wanted to go crazy and have a service chain of 16 functions, then it will still be one SID.
Okay, understand. Thank you.
Do you need to add some comments to this?
Boris?
Hi. A short question. You mentioned what MacLeaf creates SR policy. So how does it create? I mean, like, is it statically pre-configured or it's somehow dynamically provisioned?
That's the logic of the control plane. So I actually, since I'm not dependent, I can do whatever we want. We actually can do like netconf-based policy creation. We can do PCE. We can do gRPC API if it's API capable. As I said, I could actually do GitOps with Ansible. That's one of the capabilities that SRv6 gives me, independence with any control plane.
But which one do you currently do?
At the moment, we did like earlier on, we did netconf plus route coloring.
Okay.
and
So BGP
we're
plus-
evolving to APIs.
Okay, got it. Thank you.
Jingi Shah, Futureway. Just quick question, Dan, on the, going back to your previous one, I found that really interesting. Are you using the arguments in the SID to tell you where you are in the chain?
No, we did a custom implementation in the data path to know where we were in the chain.
Okay.
But because it's a programmable data path, we can actually, depending on, at the moment, the data path had limit about how we could pass traffic across. But if you have more capable data path capabilities, more resources, we can do this, the arguments.
Yeah, great, thanks.
Cheng?
Johnny from Huawei. So I saw you do define a new behavior called N.SC, though I checked the INA and draft and I found out nothing.
Yeah, it's,
Yeah.
and
So
actually,
what's
it's
the
not-
so
I
what's the
don't need
difference?
to.
Yeah.
That's-
So what's the difference between your behavior and the N.NSH divided in your RFC 94?
Well, if you get, and if you go into the NSHs, there's a mapping between a SID and an SH header. Me, it's like, it's a local behavior. Like the logic is if I send an IPv6 address to a Linux kernel or any kind of programmable device, whatever he does with it, it's internal to him, you don't care. So that's the logic of the N.FC. It's a local SID instruction. Whatever I decide to just count bits or decide to pass traffic, or it's basically a local behavior. So that was to us the logic of the network programming. So I don't carry the SID capability independently of the device. It's just a local operation.
So looking forward to a new draft. Yep. Thank you.
But it's the first come, first serve registry, right? This one. So I think you should register it anyways. Yeah, Ketan.
Hi, Ketan Talalikar, Cisco. Thanks for sharing this. And to answer that, I would remind that there is a private use in the segment routing registry. So operators are free to define their own special sauce and do it that way. It doesn't need standardization. Probably that's
Yeah.
what you're doing.
Okay.
I wanted to go back on the feedback for some of the work that is in IDR, which you perhaps I would like you to ask you to share your inputs there. And if something is not necessary, I think your inputs will help us
Do you want me to do it on the mic or on the mailing list?
anywhere. Thank you.
I'll do it on the mailing list, but the logic for me was, and I was part of the LS services draft, is that well, we actually have trouble already having functions like network function or service functions just supporting Yang. Then having them to try and like now do BGP-LS. Like think about this, having a DDoS engine that is fully secure, start doing BGP-LS to expose that you exist. The logic, if you ask any kind of security function designer, will say, I don't really care about that. I don't want to go there. I don't want to be aware. So the logic is, to me, that it's fine from a protocol perspective. I want to expose everything to LS, but the reality is these kind of devices don't follow those rules.
Thanks, Dan.
Thanks so much for sharing your experience. I hope you can also contribute with documents and give us the same kind of guidance that you have so well articulated today.
Perfect. Thank you.
You can introduce. No, just introduce.
That's okay. So, Jiangang, could you hear us?
Yes.
Okay. So Jiangang is from China's Southern Power Grid. I think this is a very interesting topic. So Jiangang, please go ahead.
You also have the slide control, so you should be able to change slides.
Okay. Can you see my screen?
Yes, please go ahead. Yes, please go ahead.
Okay. Good afternoon, everyone. This is Lu Jiangang from China Southern Power Grid. Thank you, Chairman, for this opportunity to share our SRv6 deployment experience in power grid network. The picture of this slide is the iconic building in Guangzhou named Guangzhou Tower. Wish and welcome all of you to visit Guangzhou. It's my pleasure to share some understanding and experience about China Southern Power Grid, how to build up a future-oriented SRv6 network for power grid. First, I would like briefly introduce the network of China Southern Power Grid. CSG provides power supplies services for 5 provincial level regions in South China, as well as Hong Kong and Macau. The IP data network is one of the most important part of China's Southern Power Grid. Fundamental infrastructure connecting substations, service center, power supply station, dispatching center, and so on. The whole IP data network of China Southern Power Grid could be divided into 3 levels: group backbone network, province backbone network, and the regional access network, connecting the 5 provinces and CSG cloud. Physically, there are 3 isolated networks with this 3-level architecture for different services based on security requirement. Dispatching data network, integrated data network, and voice video network. Now we have more than 230 regional data networks, over 50,000 nodes with more than 55,000 network devices. This page shows the motivation of deploying SRv6 in our network from 2 aspects. One is new service requirement, and the other is the potential limitation of existing MPLS network. For the first point, SRv6 could be used to improve network SLA. There are mainly 2 types of new digital services in power grid, which raises more critical network requirement. One is power grid digitalization, of the other is the fast growing green power plant. For the second point, the massive LOT terminals in power grid request IPv6 to provide a large address space, which could not be provided by MPLS networks. And we also would like to highlight the advantage of SRv6 about protocol scalability and simplification in large networks. Take substation inspection services as an example. Now we use analytic monitoring in 500 kilowatt substations, while real-time video surveillance and massive status check IoT devices. In one substation, there are over 200 4K cameras, 2 more inspection robots, and over 30,000 checkpoints via IoT devices. On the other hand, massive green power plant, such as solar power plant, wind power plant, connected to power grid, and these energy are not stable. That requires high frequency and real-time power dispatching to keep generation and consumption in balance. This scenario requires scalable IP address space, high availability, and SLA guarantee. Based on the motivations above, we would like to share our SRv6 deployment experience in 3 key scenarios. In the first case, I will introduce how to achieve compatible migration with existing MPLS network and SRv6 new network in such large-scale network. In the second case, we will discuss how to transport the bustling traffic via SRv6 load balancing technology to improve the bandwidth usage. The third case, I will introduce how to guarantee the critical services SLA performance. The first scenario is about migration. In 2022, China Southern Power Grid began upgrading the dispatching backbone network. During this project, we encountered a challenge. The network comprised a large number of devices, each with different lifestyles, life cycles. This complexity prevented us from migration to an SRv6 only stack in a single step. To address this, we utilize the fact that all dispatching services operate between substations and the dispatching center. We decided to upgrade the dispatching backbone network based on regions. Firstly, we upgraded the aggregation nodes and core nodes and developed MPLS L3 VPN and SRv6 EVPN with IPv4 and IPv6 dual stack. For the upgraded nodes in access layer, it developed SRv6 EVPN only in IPv6 single stack, and all services migrated to SRv6 terminal. For the existing access nodes, keep MPLS and interconnect with aggregation core layer in MPLS terminal. Via this strategy, the dispatching backbone network migrated to SRv6 and is compatible with the existing MPLS network. And as all the existing nodes being upgraded, the network will turn into SRv6 only. This upgrade strategy helps to simplify the network interconnection between the new and the existing region. The second scenario is about load balancing. China Southern Power Grid is now promoting smart inspection and for the substations and accelerating the deployment of video surveillance. This table outlines our plans for substation video surveillance, which includes over 500 cameras in 500 kilowatts substations and more than 300 cameras at 220 kilowatts substations. All substations operating at 220 kilowatts will transmission to unattended operations, replacing on-site inspections with radio surveillance. These changes will result in a significant increase in data traffic within the network. The SRv6 policy, utilizing multiple seed lists, will enhance bandwidth utilization, particularly to accommodate the surging video surveillance traffic from substations. For example, at the Guangzhou 220 kilowatt substation, the deployment of an additional 100 cameras for real-time monitoring increased the bandwidth requirement from 20 Mbps to over 100 Mbps. However, the existing network lacked of a 100 Mbps path. With SRv6 policy, we can deploy a candidate path using two seed lists, one for the 20 Mbps path and another for the 80 Mbps path. This approach allows the SRv6 policy to split traffic into 20 Mbps and 80 Mbps segments, meeting service requirements effectively. Another application scenario arises during annual typhoons and rainstorms in Guangdong. During these events, emergency support is essential for monitoring on-site conditions via video surveillance for various teams, including.
Time is limited. Please
Okay.
speed up.
I go fast. And the third scenario is about path optimization. The introduction of new services in the power grid has raised the critical network requirements, such as the need for telepresence, conferences, and remote technical support, where network delay must be kept within 15 ms. By integrating SRv6 with an SDN platform, we can achieve flexible adjustments to SRv6 policies based on latency and bandwidth usage. The SDN platform continuously monitors service as LAS. And in a summary, our experience shows that SRv6 is not limited to be used in service providers only. It also can play key roles in supporting critical operational technology and emerging digital services with large enterprises networks such as power grid. As we continue for SRv6,
Jiangang, thank you. Thanks for sharing your experience. We really welcome it. Are there any questions? Otherwise, we are running a little tight. Are there any questions for Jiangang? Yes, we have Boris. Go ahead. Quickly.
Yeah, short question. For first use case, you said what old access segments still use MPLS. So did you upgrade your P routers to support SRv6 MPLS interlocking?
Boris, could you type that in the chat? I think that would be
yeah, surely. Okay, thank you.
Okay. Are there any other questions? Otherwise, we'll move to the next presentation. But we really thank you for coming and sharing your experience.
Yeah. Okay, so next one is from Thomas. Yeah. Thomas,
okay,
please.
thank you.
So, hello. Hello. Hello, everybody. So I'm from Swisscom, and I would like to share with you an SRv6 network incident network analytics postmortem. So this is not about the network incident itself, it's about analytics. So basically how the incident has been observed by our network observability system, and it gives insights what happened within Swisscom at a particular moment in time, what kind of operational metrics we are collecting from the network, and what analytical insights we are deriving from it, and how we are handling overall the situation, and also at the very end, what kind of improvements we can bring into the system, but also into the network protocols which are being specified here at IETF.
Not moving?
No, now it's moving. So so there are different network analytics use cases, and today we are focusing on network anomaly detection. Network anomaly detection requires network telemetry real-time transformation. At the bottom, you see based on the network telemetry framework, which protocols are we using for collecting those metrics from the network. And in the middle layer, you see various NMOP drafts, which are describing the integration into data mesh. So here in this slide, we are describing just briefly, it's about holistically collecting network telemetry metrics from the network. So throughout the segment routing domain, so in the edges, but also on the core nodes, we are exporting on all three network planes data through IPFix, PMP, and YANG push, and we make them correlatable towards the service inventory, where we are maintaining the so-called logical connections and connection points. So it's a layer 3 VPN and their endpoints. The focus on network anomaly detection is we need to recognize operational and configurational changes for a given connectivity service in the network faster than our customers. That means usually well below 7 minutes. And also we need to bring, therefore, since this is not humanly possible, we need to automate, therefore, the network observability. And last but not least, since anomaly detection requires a refinement process to reduce the amount of false positives, we also have to define an automation on that level. On the right-hand side, there are 3 documents which we are currently discussing at the NMOP working group: an architecture, the symptom semantics, and also the lifecycle definition, how the lifecycle can be further optimized. So let's get started. On the right-hand side, I give briefly an introduction into the timeline. So it's related to a network maintenance window, which happened early in the morning. And there were configuration changes being performed in the ISIS domains on the ABRs. So there was a migration from L1, L2 to L2, L2 on the ABRs and also the connected PE nodes. In total, there were 15 configuration steps. And once the maintenance window was started, throughout the maintenance window, we observed on various levels, basically in the forwarding plane, in the control plane, changes in the network. And those changes in the network were actually negatively impacting the forwarding of the packets, or negatively impacting the connectivity service. During that maintenance window, we got 2 calls from 2 different application teams. One application team described that the voice over IP service is impaired, while the other application team, who is responsible for provisioning the mobile subscriber services, they notified the team that basically the provisioning is no longer possible, so they have reachability possibly to their LDAP system. During the maintenance window, the causality could not be found out, so the responsible network operation team did not find out that actually the change in the network and the impact on the application level is related to each other. Later than that day, during the day, they did a further analysis and also requested additional support from the analytics side. And then this is when basically the post-mortem process started. On the left-hand side, what you see in front of you is our analytical metrics. So this is produced from the anomaly detection system. Here we are grouping several connectivity services together. You see different anomaly detection checks, which I will describe in detail in the next slides. And on the right-hand side, you see the so-called concern scoring for the different checks we are doing on those VPNs. Here I need to highlight we have approximately 12,000 layer 3 VPNs, and they are 7x24 with this anomaly detection system concurrently being monitored. What's being important is for a monitoring system, especially in network observability, that we are getting the right data out of the network. That sounds easier than it is and requires some innovation. And usually with innovation, just having an idea is not enough. It goes basically from a envisioned state to an operational accepted state. So there is a transformation happening not only in the industry itself to make those data accessible, but also on the network operator side in using those data. And here, like for instance, in IPFix, Swisscom was involved in the standardization of the IPFix SRv6 visibility. In BMP, we are also involved in the standardization to get access to all the different RIPs in BGP, but also in BGP into the best path decision process and also into route events, so that we are understanding when route policies are dropping certain paths, how this is basically influencing the BGP best path decision, and then consequently also the passes being installed in the RIP. On the Yang push side, here the things which we are currently doing at IETF in bringing Yang push more closer to the data mesh are not yet operational in our network. So it's more up and running now in our lab environments, but we expect throughout 2025, 2026 that this becomes also operational in the network. So let me give an example on the application side. So I was in the beginning mentioning there were two application teams were having problems to find causality. So here in this query, which we are doing in the time series database, we are query first on the BGP community, which is related to the layer 3 VPN. And from there, we are filtering down specifically to the layer 4 properties of that transport session and showing here that basically the TCP session that we have at a particular point in time where we had the connectivity problems. We have SYNs and resets on those transport sessions. On the right-hand side at the bottom, you see then the consequent impact when we can no longer provision the mobile subscriber services, that the responsible network element had to go into a fallback mode and provision fallback profiles. Here, a similar aspect, but now on a different application that's related to the voice over IP service. Here we are matching on a different layer 3 VPN connectivity service and a matching on the voice over IP control plane traffic. And we can see that here we are looking at the flow count properties. So flow counts is the amount of flows or the amount of transport sessions we have. So at that particular point in time where we experienced the connectivity service impact, we had a lot of retransmissions. Now we are changing into the BGP control plane, and for a particular route distinguisher, so a route distinguisher is a VRF on a network node, and we can see throughout the time window changes in the BGP topologies. It was always an update on the topology, but exactly on the point in time when we saw on the previous two applications where we experienced the connectivity service impact for a brief moment in time, we did not have a pass for that particular VRF, and that led to forwarding plane drops. Here on a layer 3 VPN, these are like the basic operational metrics we are collecting. We can see the so-called BMP route monitoring, so the BGP route monitoring changes in the network in the overlay. We can see from a forwarding plane perspective that we have missing traffic. So we are dropping outside of the monitor domain. That leads to decreased amount of flow counts, so less transport session. And within the monitored domain, we can see also some forwarding plane drops. So that means that the NPU on the responsible network node was dropping the device, and we see also the reason codes why the packets are being dropped. At the very bottom, we get some insights into the MPLS, into the SRv6 P core itself. We can see the shift of the traffic among the different nodes, and on the right-hand side, the SRv6 tunnels, basically from which SRv6 node to which SRv6 SID container we are forwarding the traffic to. Yes. So that's at the end what the anomaly detection detected. So we detected in these various checks what we have seen in the operational metrics. So the detection worked according to plan. Here, another example from another VPN. And here, the analytical results. The results, we were not very happy, and that's due to the auto-profiling, which was not present at that point in time. And we have so-called replay capability. So we replayed the data a few days later when we had already the new auto-profiling feature developed. And we can see that now the checks where we anticipated would be better with the auto-profiling were apparently being better, except one, which we are now currently further refining. That shows a bit the life cycle process you need on anomaly detection to getting the results which you're expecting. Another very important aspect is lab. So if something is not going well in your deployment in production, you're going back in the lab. Important is data. So you want to reproduce exactly the same incident in your lab environment as well. And here, the data which you're collecting through network telemetry will help you to confirm that your lab reproduction is actually successful. And it means basically the dashboards you've created for your maintenance window in production can be easily adapted in your lab environment. So there is a lot of things to be improved. I'm just highlighting one or two things which went well and which went bad. Which went well is we can recognize those incidents well below 2 minutes. Mainly the 2 minutes delay comes from the IPFix aggregation in which we are performing, which is delaying the metrics. So we are in the expected range. It also shows our focus, which we did, is on focusing on the SRv6 data plane in the core network paid out in here. We were able to recognize the drops within the cores. What didn't went very well is we could see that basically the teams involved in network operation, they are not used yet on monitoring on a connectivity service level. Therefore, the application colleagues and the network colleagues who were performing the change in the network could not see the causality between the two. And I would say that's it. Let's stop here.
Yeah, quick questions. We are running a little late. Any questions for Thomas?
Maybe we can list the question in the checkbox because the time is limited.
There are no questions, but Thomas is here. Let's use our mailing list if you have further questions on this. This is a very interesting case. We have in our charter an item on network observability. So this could be a foundation for us to figure out what guidance we want to say in this term. So, and Thomas, we are looking to you that you will be able to provide that input to the working group.
Absolutely. And also, if you have interest in this area, please reach out to me. Thanks.
Yeah, thank you, Thomas. So next one is Gang. Gang, could you hear us?
Yes, can you hear me?
Yes, Gan, and I'll give you the slide control.
Yeah, the time
Okay.
is limited, please. Yeah, go ahead.
Durav, how do I control the slides, I guess, from my end? Oh, I just click the button. Oh, I see, to go to the next page. Okay, cool. Perfect. Okay. Hi, my name is Gian Mishra, and I'm presenting on SRv6 in use in the Verizon IT data centers. Next slide. Oh,
You
sorry.
can control. You,
Yeah, sorry. Sorry about that. Okay, so our Verizon network, it compromises of made up of a large number of smaller networks in our single administrative domain. Um, delivers cohesive service offerings to many to meet customer expectations. We use a variety of protocols: RSVPTE, SRMPLS, and SRv6 to manage our network traffic. And we cater to consumers, businesses, government entities, handling both wireline and wireless traffic across a vast range of services. In this presentation, I'll be focusing on the bottom corner, which is the SRv6 in our corporate internal network, so our IT network. Uh, in our last presentation that was given by Louis with Verizon, he had gone over like our strategy and overall Verizon. We're embracing SRv6, and it's something that we're looking at. There's a lot that we can benefit from SRv6, and in this presentation, we're focused on our corporate IT and some operational considerations that we actually came across and would like to share with the broader community with the SRv6 ops and so forth to see what we learned, our learnings through our journey with SRv6. So our journey with in our Verizon IT data center. So we originally started out, it was like let's say a big, huge layer 2 domain. And then it was basically one big fault domain, but we wanted to break it down and not just have one large fault domain, break it down into smaller fault domains. So what we did was we took our data centers and we carved them up into pods. So in basically creating a multi-pod architecture. So we had in most of the data centers that range from between 5 to 10 pods per data center. And then as we evolved, this was when we did it initially, it was a layer 2 pod. So, but we broke up that larger L2 domain, like one big fat switch, into multiple layer 2 pods. And from there, we evolved into a VXLAN class architecture, which we have today. And then from there, we actually started on our SRv6 evolution, our journey to take that same multi-pod architecture, but evolve it into an SRv6, but with that same cloth fabric multi-pod architecture. When we were starting to develop that and come to a the solution was one of the ideas that came up is, do we really need to have the multi-pod, and is multi-pod relevant to SRv6? And really the big thing with multi-pod, when we initially had the layer 2 domain, it was relevant when we actually broke it down into smaller fault domains. So the concept of fault domains and using the BGP construct with a BGP-AS per pod, it does limit the size of the fault domain. So in the end, it actually ended up being very relevant, and we actually ended up keeping our same pod architecture that we had with the class architecture that we had with VXLAN. We kept the identical architecture with our SRv6 plans. One of the considerations was could we actually save on cost, like your capex costs, and maybe shrinking down to maybe a lesser number of pods, but because the fabric itself is made up of a spine and border leaf, and spine, border leaf, and leaves, but the add-on for each cloth layer would really be your spine layer and border leaf layer. So because it was nominal, and really the large heavy lifting or the volume of devices that is at your access leaf layer, there wasn't really much of a cost difference. So it really just made sense to keep that pod architecture. So it's basically it's an AS per pod, and we have many ASs that we're now wanting to be able to have SRv6 east-west connectivity across all of these pods. And with this design, we had a requirement to have VLAN anywhere. So, and being able to do VLAN anywhere across all these pods with SRv6.
Gyan, you have 5 minutes, so you have to speed up.
Okay, yeah, thanks. So with our deployment, we have so why SRv6 Nexted. So on this slide, it just shows a list of reasons why: data plane extensibility, data plane stitching. I'm not going to go through each one of these in detail, but there was quite a number of reasons why we chose SRv6. One of the big ones is to be able to extend the data center fabric to the host fabric, and that was really the big one as reasons why. So as we were going through evolution and actually testing, doing some R&D work in determining being able to have SRv6 connectivity inter-domain, between our ASs, so between our pods, so pod 1 to any other pod, what we realized, there were some operational considerations that we came across that were challenges that we needed to overcome. What we found was there was an operational guidance that we came across, and this is defined in RFC 9252, which I'll share as well. And it was basically to be able to signal that service SID. So your service SID, propagating that service SID from ingress all the way to egress to that endpoint domain. So being able to propagate it. And it's a simple change. It basically is next hop unchanged on any of your eBGP ties on both ends of the peering connections, requiring a next hop unchanged. So that's on the border leaf to the DCI and the DCI to the border leaf. So this is documented in RFC 9252 at the bottom of section 2. So basically, in order to propagate this SID end to end, and it's a BGP service overlay thing that is the operational consideration, and it's a simple solution. So if you don't do that, what ends up happening when the next hop changes, the service SID changes, the label changes, then that service SID changes. What happened? It ends up the SID manager on the local box, he automatically generates a SID, and so that SID ends up not being this incoming SID is not propagated, so it actually changes, and that's the operational consideration requirement. So the simple solution, so on the inner domain ties, basically next hop unchanged. On the IBGP peering from your ASBR to the route reflector, where traditionally for option B you would do next hop self. But now because it's doing a reroute of the next hop, the SID does not get propagated. So that's the other operational consideration, that you would have to do a next hop self. And then of course, locator reachability, advertising your locators between the domains. So the next few slides just kind of shows the operational guidance. So what happens when you're going on an inter-AS boundary, when the next hop changes, the label changes, the service SID changes, and then the SID is locally generated. So now when you add the next hop unchanged on both ends of the peering connection, now the SID is preserved, and now you've got the end-to-end signaling. So it's a very, very simple solution. The same goes with the IBGP. Instead of doing a next hop self that you would traditionally do with option B, now you do a rewrite. Now you actually just remove that. And now, so you don't do a next hop self, and now the SID is preserved. So now the SID from ingress to egress, the service SID is propagated end to end. So I have a draft, and I had mentioned it earlier. I was on the previous meeting about a draft that I have on interdomain routing. So this draft goes into detail about the eBGP. The consideration of doing next hop unchanged on the eBGP interdomain boundary, as well as on the PE to route reflector peering, where you have to not do the next hop self. And so basically a quick summary and takeaways is what I mentioned is that really the crux is on any interdomain boundary, and it's both ends of the peering connection, that you have to do a next hop unchanged. On the IBGP peering, it's not do the next hop self, and that's really the main thing. And then now that service SID is propagated, it's signaled end to end, and that's really the crux of it. And my last slide here, sorry, my last slide here is I have a SRv6 developer consortium that I've worked with, just co-founders myself and Bruce McDougall with Cisco. We have a SRv6 Lab GitHub, and this has a lot of the work that I presented today. It's all on our GitHub that has all the configs. Everything is done in a virtualized XRD router container platform. And so so that's all contained on the GitHub. It has everything that was done that I presented. I get a link to MPLS World Congress, but it has a lot of detail, a lot of information there, as well as I have a series of YouTube videos on a YouTube channel that goes into details. It goes into some really deep into use cases of SRv6 as it relates to intradomain routing. And then at the bottom here, I just kind of show the different topologies. In this one, it's the data center case studies that I've worked on, and this is related to all the R&D work that I did related to interdomain routing.
Thanks, Gyan. Are there any questions for Gyan? Go ahead, Jeff.
Jeff Tansur, NVIDIA. One comment related to traffic engineering in data center. I'm yet to see any data center that requires traffic engineering that really brings gains of having kind of centralized controller on top of cloud topology, and it's really worth it, given the amount of bandwidth that's there, that it's kind of densely meshed topology and the dynamicity of the flows. So the feedback loop is really short. By the time you talk to the controller reprograms you, the flow is already gone. So why bother in data center specifically?
Gyan, do you want to respond?
Yeah, sure. So in the data, yeah, sure. So I think one of the big benefits of having micro SRv6 in the data center is that you're able to extend the data center fabric to the host. So now the hosts are part of the SRv6 ecosystem. So being able to leverage that and being able to take advantage from the host perspective, being able to steer and traffic engineer. In your question related to the traffic engineering, there, even though you may have a lot of bandwidth, there are cases, and because you're limited to the hardware platform and the queuing capabilities of the hardware platform, there are issues related to head of line blocking, which can be solved with virtual output queues and other types of queuing, which may be on chassis-based platforms that have a lot of buffers. But even though you may have, let's say, 400 gig and you have tons of under the floor fabric, you are constrained
Jeff
by.
has a follow-up quickly.
It's really about feedback loop. By the time your controller reconciles the topology, recomputes new topological information, pushes it down, the congestion is probably already gone. You already dropped 400 gig worth of traffic. I mean, you might do something local, but specifically looking at centralized SDN solution for this amount of bandwidth and mostly really wide. We are talking about radix of potentially 256, 512 paths. So again, I don't think there's enough gains of doing centralized control to that to implement something like that. And it's really complex.
Yeah, Jeff, let's take this on the mailing list. I think this is a very good discussions to have on the mailing list. One thing to Gyan as well as thinking about whether the document that you are currently saying that it's an operational guidance, or is it more like a deployment scenario? So it's something in between. Is it more about how in a multi-pod scenario you use an existing feature, or the guidance part is very specific that I need to just configure the next hop unchanged. That doesn't feel like an operational guidance to me, but like, let's have that discussion again on the mailing list. Thanks everyone. Sorry for running a little bit over and taking some of your break time. Thanks for being here. Reach out to chairs if you have any feedback on the session and how we can improve. We are here to listen. Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Yeah, 4 minutes over. It's okay. That one is fine. This much happens. Even when you plan everything. The planning is like, not something is going to go a little bit over. Oh, but I do understand. Like, no, it's so difficult